Okay, so we're moving a lot of devices to be essentially eventually towards the use of functional thin films. So we can see that here where we're moving sort of solar cells to optophotovoltaics, incandescent to fluorescent light bulbs to light display these OLEDs and transistors to these flexible ones. And we're doing that because they have a series of unique properties, such as their flexibility, the fact that they're made of more environmentally benign materials, and the fact that they could be very easy to manufacture. So here we have a schematic of an OLED with a model of the emission layer. So you can see the emitter molecules here embedded in our host matrix. And the first practical OLED was made in the late 80s. And since this was made like about 30 years ago, we have the question of why haven't we moved ahead more quickly to implementing them in our homes and our devices and so on. And the reason is that there's a couple of key issues that we have to contend with, such as the control of the morphology. These devices' function and efficiency is heavily dependent on the morphology, the long-term stability of these devices, and the manufacturing complexity. We can make these devices with quite high efficiency with vacuum deposition, but that's expensive. Or we could use a solution processing, but then we lose the fine control of the morphology of these devices that gives them that high efficiency. So there seems to be a balance that needs to be struck there. So in order to sort of improve our understanding of these devices and how they function and how we can improve their efficiency, we need to ultimately understand the morphology of these devices. So a lot of work has been done in characterizing the morphology using experimental work like neutron diffraction, like GWAX. But unfortunately, these things can't give us the whole picture of the morphology of the devices because it's limited to a spatially and ensemble average properties. So we need to use something else. And what we can do is model these. So like the local morphological features, we can't really access them using these experimental techniques. So things like whether they're completely amorphous or whether they have crystalline regions or voids, what the distribution of the molecules throughout these thin films look like. Are they evenly spaced? Are the certain molecules aggregated at different interfaces, or are they percolated throughout the system? Also, what do the alignment of the molecules look like? So you can see here that if the transition dipole moments are parallel to the substrate, we have an emission layer that has a much higher light output than an emission layer where the transition dipole moments are randomly orientated. And we can see the effects of the manufacturing process here. So if we have deposit a typical host material like CBB with vacuum deposition and chloroform using solution processing, we can see that initially they look identical, but over time, the vacuum deposited system remains stable, but on the first phase of the solution process chloroform, there is a formation of a crack, and over the second phase, there's the formation of microcrystalline domains. So how can we get a better picture of the local morphology and how it might affect the function of these devices? I've chosen to do it using modeling, using particularly electrodynamics, where I can represent how these, I can accurately represent how these systems evolved using different manufacturing techniques over time, so I can create an accurate final morphology in atomic detail. And one of the first systems I was involved in doing this was modeling the vacuum deposition of bulk heterojunction with a low donor concentration. So we have this image in our head of what a bulk heterojunction normally looks like. So with a clearly defined domains of acceptor and donor material. But that might necessarily not be the case. Yeah, so, and here we see the molecular dynamic simulation of the vacuum deposition of this device. So you can see the bucky balls sort of bouncing down off the graphene substrate back up into the air. You can see that they sort of have to cling to previously deposited TAPC first before they can sort of grip on and start building the layer. And you can see sort of the roughness of the surface of this system and sort of the pores that are being left behind. And also perhaps some circulation of the donor material throughout the system. So I modeled the vacuum deposition of these thin films at different weight percents of the donor material, as you can see. And we can see that over an increasing weight percent of the donor material, we have a reduction in surface roughness of the thin film and a reduction in the porosity. So we can make the leap that an increasing amount of TAPC helps lubricate the system, and we end up with a more dense and more layer. Now, what about the idea that a bulk heterojunction with a low donor concentration is still quite efficient? So with the TAPC here, if we assume that the hole can move from these different highlighted points that are red, we can build an image of what the percolated network is from the bottom of the substrate. So once it stops, there's no pathway for it to keep moving throughout the layer. Yeah. And at 1 weight percent, we can see the networks stop quite close to the substrate, but at 5 weight percent, assuming the B holes can about 1.3 nanometers, this network penetrates quite deep into the layer. So we have an answer as to why a bulk heterojunction with a low donor weight percent can still have quite a high efficiency. Another system that I have been interested in is the solution processing of an emission layer in an OLED. So I chose to use an archetypal system so I could compare the morphology to experiment. So I chose a host material PVP, the emitter was AUCAOS, and I chose to solution process it in chloroform. And there are a couple of issues to contend with when modeling the solution processing of the system. For one, this system is extremely large. It has 2 million atoms and would be quite computationally expensive to run. We also had to contend with the idea that there were also worries that the chloroform might not evaporate at all. But the chloroform did evaporate, as you can see here. It did spontaneously leave the solution, and you can see the gradual depletion of the chloroform here over time. And we wanted to model this as accurately as possible because I wanted to see how the thin film formed over time, because there were proposals that the rate of chloroform removal would be such that the concentration of the solute would increase uniformly over the entirety of the system and eventually lead to a phase separation akin to spinodal decomposition. But as you can see, that isn't the case. Instead, there is a formation of a skin at the solution vapor interface that remains constant until the thin film becomes dry and the substrate and the thin film meets the substrate. And this is illustrated graphically in this image here, where we see the density of the solutes along the z-axis, so along here in the system. And we can see it at different points in time. So you can see here that the density of the crust remains actually quite constant quite early in the simulation, only decreasing a little bit over time. And the solution beneath this layer remains constant until the film begins to dry. And you can see that slow increase in the density here. But there is still quite a difference in the final layer between the density at the skin at the surface and throughout the layer. So what's going on here? are there voids, or is there a significant portion of remaining solvent? And there is solvent remaining in the system, and it appears to be sort of aggregated at the bottom of the system. This is quite a significant amount of solvent. How long might this take to escape? So in order to see how long this might take to escape, we measured the mean square displacement over time, which is proportional to the diffusion of the chloroform through the thin film. And we did this at different weight percent of chloroform in the system. And as you can see here, as the weight percent of chloroform decreases, the diffusion of chloroform through the system decreases quite dramatically. In fact, if you graph the log of the diffusion of the chloroform against the reciprocal of the chloroform in solution, we can extrapolate how long it might take a chloroform to diffuse through a 50 nanometer system. So at 10 weight percent, it takes 6 milliseconds, and at 5 weight percent, it takes 2 minutes. And this, this is quite a thin film. These films can exceed 100 nanometers. So at 1 or 2 weight percent, this might take hours to days to leave the system, and in fact, some chloroform might remain trapped in the film, affecting the function of the device. There is also the question of how does the removal of the solvent affect the morphology of the thin film, because when it leaves, it will leave voids. So here you can see the density of the solutes in the system when the chloroform still remains in the system. We can see it's quite a spike here, which indicates an increased density at the base of the substrate where the CVP are likely more aligned. We can see this sharp decrease here where the solvent is, and these increase in the density represent. So once the solute was solvent was removed, it was allowed to relax for 400 nanoseconds. And you can see here that these voids do collapse. And what degree do they collapse? They collapse such that they are equivalent to the density of a vacuum deposited system. And this would lead to quite a large amount of stress on the thin film. And this could explain the formation of a fissure over time. And of course, chloroform remaining in the system would aid in the formation of microcrystalline domains. Now we have these very detailed models, and we can use them for a number of different things, including understanding the color of the output light in an emission lamp. So if you want to make a white OLED, you have to use different colored emitters such as green, red, blue, or blue and orange. But it's not as simple as having a 1-to-1 ratio of orange to blue in a system, because these excitons can transfer to a different colored emitter. So it's useful to have these models because the rate of transfer and how often these excitons transfer is heavily dependent on the local morphology of the system, and extremely dependent on the distance between the donor and acceptor molecule when it transfers via mechanisms such as FRET or DET. In fact, in FRET, the rate of transfer is inversely proportional to the distance between the acceptor and donor molecule to the 6th power. And you can see this quite sharp decrease in the rate of transfer by this example equation here, where we have the inverse to the 6th power. I'm also interested and have been using these models to simulate the penetration of water into thin films with Abhay Sharma, because of course the penetration of water into thin films can lead to things like degradation. And we're also extending the solution processing of different thin films to include dendrimer thin films. So I am currently running simulations where the host material is TCTA, and the emitter molecule is the dendrimer, and the solvent is toluene. And we can see how these different molecules affect the formation of the thin film and the final thin film morphology. So in conclusion, the simulations captured key features of the mechanism and growth of the morphology. We could see nucleation at interface. We can see that perhaps there is trapped solvent in these thin films over longer periods than we expect. And we can see that voids do not remain in the system, they can put stress on the thin films. And we're exploring water penetration into these thin films and the solution processing of much more complex systems. And we're also working on expanding the timescales and dimension of these simulations so we can have better comparisons to experiments. I'd like to thank Professor Alan Mark and Paul Burns for supervision and support. I'd like to thank the MD group and COPE and NCI for providing computer time and the ATB for finding the small field.
Thank you. Thank you for a very interesting seminar. So we can open up now for questions from the audience. So if you have a question, can you please unmute your microphone and jump in and ask the question? If anyone has any questions.
I have a question.
Yeah, please go ahead, David.
So the evaporation rates that you've looked at are, I guess, much faster than experimental evaporation rates. Have you tried simulations where you do different evaporation rates to see how the quantities that you measure, how they vary with the evaporation rate?
No, I haven't. So this, so the chloroform left spontaneously, so I didn't necessarily have any control over how fast the chloroform would leave the system. And if I think if I did choose to limit the removal of chloroform to their actual rate, the systems would become too long to actually do the calculations on. The solution process one you see here took 3 months of calculation.
Okay.
So no, that's something I haven't looked at yet.
I mean, I guess you could speed up the evaporation by using a higher temperature.
Yes, so this was done at 310 Kelvin, so just a bit above room temperature.
Okay, thanks.
Could I comment just a little bit on that as well? The models reproduce the heat of vaporization very accurately, and also the excess free energy also very accurately. And so the rate of evaporation that we're seeing should actually be very close to the actual rate of evaporation of this system in vacuum. So if we wanted to slow it down, we could put on a vapor pressure. But actually, I think these rates are quite realistic if we're actually forming these systems in high vacuum.
Okay.
Yeah, so I guess that leads to the question, like, would you speculate about any differences you might see in the morphology if it was actually done with a realistic vapor pressure above the film?
I suspect we probably see the formation of the skin be a bit slower. The solute might have more time to diffuse, and we might see less of that skin, I think.
Yeah, yeah. I just wonder, whether these are, I guess it's always very tricky to know, right? What consequence that would have in terms of the overall interpretation of the results. But yeah, this is already 3 months of computer time. So yeah, there's obviously not that much more room of what you can do, right?
No. unfortunately.
Did we have any other questions from our audience? If not, then everyone please join me in thanking our speaker one more time. So yeah, very